use the second derivative test to classify all critical points for the following function in space. And here we are given the function f of xy is equal to 8xy minus 2x to the fourth minus 2y to the fourth. So, the very first thing that we need to do here is find the potential critical points. So we want to find the potential critical points. Now, to find these potential critical points, we need to solve the system of equations created by setting the first order partial derivative with respect to x equal to 0, and the first order partial derivative with respect to y equal to 0. So we want to solve this system equations for potential critical points x, y. So here we go. Let's find the first order partial derivative with respect to x. So this is going to leave us with 8y minus 8x cubed. Now notice here we have a greatest common factor of 8. So I'm going to pull that 8 out. So we now have 8 times y minus x cubed. Beautiful! Now finding the first order partial derivative with respect to y, here we treat x like a scalar. So this is going to leave us with 8x minus 8y cubed. And again, we see that greatest common factor of 8. So we can factor that 8 right out. So we have 8 multiplied by x minus y cubed. Beautiful. Now again, thinking back to what we're trying to do here, we want to set both of these equations equal to 0. So let's do that while we're here. We're going to set both first order partials equal to 0. So we can actually simplify this. We can divide both sides of this equation by 8, getting rid of that scalar multiple, leaving us with y minus x cubed is equal to 0. And very similarly, with the first order partial with respect to y, we're going to set this equal to 0, and we can divide both sides of this equation by 8. So again, those 8's cancel each other out to 1, leaving us with the simplified first order partial x minus y cubed equals 0. Alrighty, so we have simplified these first order partial derivatives, and we're now ready to start solving this system. So here we'll rewrite our system. We're ready to solve for the critical points. And we have the first order partial derivative with respect to x is y minus x cubed is equal to 0. We'll call that equation 1. And then equation 2 is the first order partial derivative with respect to y set equal to 0, which was x minus y cubed equals 0. We'll call that equation 2. So pick your favorite to start. I'm going to begin here with equation 1. So we have y minus x cubed is equal to 0. And notice how we have just a single y variable here. So I'm going to solve for that y. So I have y is equal to x cubed. So we'll keep this in mind now. And what we're going to do with this is actually go ahead and now substitute this into equation 2. So we are substituting this rewritten equation 1 into equation 2, which is going to allow us to solve for x. So rewriting equation 2, this is going to be x minus x cubed equals 0. And so this simplifies to x minus x to the 9th. Notice we have a greatest common factor of x. So factoring that x out, we have x times 1 minus x to the 8th power is equal to 0. And now we can solve each individual case for x. So case number 1 is x is 0. Oops, we did it. Woo! Now case 2 is 1 minus x to the 8th is equal to 0. So if we add x to the 8th to both sides, we have 1 is equal to x to the 8th. And now taking the 8th root of both sides of this equation, we are left with plus or minus 1 is equal to x. So we have determined 3 potential x values. So now that we have these x values, we want to go ahead and find their corresponding y values. So we are going to we're going to substitute x equals 0, x equals -1, and x equals +1. And we can substitute these into either equation to find y. Now, conveniently enough, the first thing we did was solve equation 1 for y. So let's use that. So we have three cases here. When x is equal to 0, y is going to be equal to 0 cubed, which of course is 0. So one potential critical point is 0, 0. When x is equal to -1, we have y is equal to -1 cubed, which equals -1. So a second potential critical point is the ordered pair -1, -1. And last but not least, when x is +1, substituting this into equation 1, we have y is equal to 1 cubed, which again is 1. So our third potential critical point is the ordered pair 1, 1. So these are our three potential critical points. So the next order of business is to classify these three potential critical points. So making sure we have plenty of room here. We're now ready to apply that second derivative test, or the discriminant, for each one of these potential critical points. So in order to apply the discriminant, we need to find these second order partial derivatives. So let's quickly recall, what were the first order partial derivatives we found? Well, we have the first order partial derivative with respect to x was 8y minus 8x cubed, and the first order partial derivative with respect to y was 8x minus 8y cubed. So for the discriminant, we need the second order partial derivative of x with respect to x, which is going to leave us with a -24x squared. We need the second order mixed partial derivative. So we have the second order partial of x with respect to y is leaving us with 8. And we also need the second order partial derivative of y with respect to y, which leaves us with a -24y squared. So we are going to use these three second order partial derivatives with the three potential critical points in the discriminant to classify whether or not they're extrema and what type of extrema they are. So here we go. The first point that we are checking is the potential critical point 0, 0. So we need to evaluate each of these second order partial derivatives at this point. So we have the first order partial derivative of x with respect to x at 0, 0 will be -24 times 0 squared, which of course is 0. We have the second order mixed partial derivative, which is 8 no matter what. And then we have the second order partial derivative of y with respect to y at the point 0, 0. So that's -24 times 0 squared, which again is 0. Beautiful! So we are now taking these evaluations and plugging them into our discriminant. So we have the discriminant at this point 0, 0 is equal to 0 multiplied by 0 minus 8 squared. And now remember, we don't care about the exact evaluation here. We just care about, is this positive or negative? So we're able to conclude that therefore, since the discriminant at the ordered pair 0, 0 is negative or less than 0, then this is letting us know that the function f has a saddle point at the ordered pair 0, 0. Beautiful. So case 1 is done. So we want to go and do this same thing for the other two potential critical points. So our second potential critical point is the ordered pair -1, -1. So we have the second order partial derivative of x with respect to x at -1, -1 will be -24 multiplied by negative 1 squared, which is 1. We have the second order mixed partial derivative is 8 no matter what. And then we have the second order partial derivative of y with respect to y at negative 1 is minus 24 multiplied by 1. So taking these numerical evaluations and plugging them into our discriminant, we have the discriminant at this point, negative 1, is equal to negative 24 multiplied by negative 24 minus 8 squared, which we can see is positive. So therefore, since the discriminant at this ordered pair, negative 1, is greater than 0, and since the second order partial derivative of x with respect to x at this ordered pair, negative 1, is less than 0, then what this is telling us is that the function f has a local maxima at the ordered pair, negative 1. Beautiful. And so we have classified our second critical point. And last but not least, we want to check the critical point, positive 1. So plugging in this ordered pair to our second order partial derivatives, we have the second order partial derivative of x with respect to x is negative 24 multiplied by 1 squared, which is 1. We have the second order mixed partial derivative is, again, 8 no matter what. And then we have the second order partial derivative of y with respect to y at 1 is, again, negative 24 times 1. So plugging these into our discriminant, we have the discriminant at the ordered pair 1 is equal to negative 24 times negative 24 minus 8 squared, which we can see is positive. And so, therefore, since the discriminant at the point 1 is greater than 0, and since the second order partial derivative of x with respect to x at the point 1 is less than 0, then we know by definition that the function f has a local maxima at this point. And we have officially classified all 3 potential critical points. Woohoo! So this is our beautiful final answer.